Greetings everyone. Today we're going to be talking about static equilibrium. By static equilibrium, what we mean is that, like if you look at this sign right here, it's not accelerating. And it's not accelerating in a linear direction or accelerating, having some angular acceleration. You could just say that it's at rest. These are the most simple kind of systems that we have, is that basically it's not moving. So this would be an object that's in static equilibrium. So what can we say about this mathematically? How can we write down and be able to solve for things that we might want to know? That's what we're going to be looking at today. So if something is in static equilibrium, what we mean is that the acceleration on this object is 0 and the angular acceleration on an object is 0. If the acceleration object is 0, what that means is that when we write out these Newton's laws that are governing the motion of the object, that we're going to get these to be equal to 0 because A is equal to 0. And we're also going to get an equation for torque. So in 2 dimensions, we're going to get 3 equations. And from these 3 equations, we can solve for whatever other unknowns that we might want to know about this object. And so that's what we're going to be looking at for 2 examples today. All right. So here we're going to be considering a problem where we're bending over to pick an object up. So we're just picking up a 100 Newton object. So this is about 10 kilograms, right? So not very heavy. And then we're going to be picking it up with our back horizontal, which is not a good way to pick things up. And we're going to find out why that is. So our back muscle, we're going to just approximate as being attached to 2/3 up our spine. So that's way up here. So this would be 2/3 L. And then it's pulling at an angle. And this angle we're going to say is about 12 degrees. So we're going to take the weight of our upper body to be about 350 newtons. And it just approximate it as in the center of this. So just pulling straight down. And then here's the object that we're picking up is pulling straight down. So we have another force that we need to consider, and that's our hip pushing against our back also. And we're just going to break that up into these 2 components. So let's talk about the sum of our X forces. So we're just going to add up everything that's to the right and then subtract everything to the left. So that's minus T cosine theta. And then this is equal to 0. So the 0 is because we're in static equilibrium. This object isn't accelerating to the right or up or down, or even having any angular acceleration. So let's look at the y direction. So we're going to have Ry plus t sine theta minus 350 newtons minus 100 newtons is going to be equal to 0. Then we have one more constraint on our object, and that's the torque. The sum of our torques needs to be equal to 0 also. And so here we need to pick an axis of rotation. And you can pick any point, but it's best to pick a point where it's going to make some of these that we don't care about equal to 0. The torque about that equal to 0. So if we pick our axis right here at our hip, it's also more natural. But now we don't have to worry about any torques created by the hip. We only need to consider these 3 forces here. So the sum of our torques then is going to be, we need to say which way is positive torque. So we're going to say if it's rotating clockwise, that's going to be positive torque. So 350 times L over 2 plus 100 times L. And then minus, here's the tension of our back muscle pulling, and it's pulling at 2/3 L, so that's our R, 2/3 L, then times T, and now what we want is the perpendicular part of this, so that's sine theta. And all that's equal to 0. So let's look back at equation number 1, and what we're going to get is Rx is equal to 0.98 T. And then looking at number 2, we can rewrite this to be Ry plus 0.21 T is going to give us 450 newtons. So here we just added up 350, 100, brought them over to this side, and then plugged in theta. And so then we can look at number 3 and start plugging in some stuff. And here I'm just going to solve for t. So here t is equal to 275 times 3/2 all over sine theta. And I actually know all this information. I know what theta is. I know what L is. Actually, all the L's cancel away. And then I just get 1900 newtons. So with actually one equation, we could find out what this tension on our back is. But if we want to know how much our spine is being compressed, we need to solve for this Rx. So here's the tension on our back. It's quite a bit of force. So now we want to solve for this Rx, and so that's the 0.98 T, and so we're going to get 1940 newtons. So that is a huge force also. So not only does your back have to support this force, but now your spine is actually being compressed just to keep you from rotating down, falling down like this. And we can also go and solve for Ry, and you'll find out that it's 363 newtons. So this right here would be like having 100 kilograms, basically, on your shoulders. So this is really why bending over by the hip and just keeping your upper body horizontal is a really bad idea, because this is a huge amount of weight right here. So if you look at toddlers, this is my son right here playing in the woods. They tend to bend down with their knees, and this way the arms can reach whatever they want to on the ground. They don't bend at the hip like adults typically do. So let's consider one more problem, and this problem is a bit more complicated. So here we're going to have a ladder. Now, the ladder has friction with the ground. This 0.4 is our coefficient of static friction. And then, but the wall up here is frictionless. So we're sitting on some slippery surface up here. So the only force that this wall can provide is a horizontal force. There's no friction, it can't provide any vertical force to keep this thing from slipping. So this ladder is going to want to rotate down and basically push this outward. So our friction is actually towards the wall. So this is our force of friction. And then we also have a force upward. This is our normal force, right? So we're just going to call that normal due to gravity. So now we also have the mg of the ladder, and we also have mg of our person. So these are all the different forces that we have. So let's look at where all these forces are, and let's do that in a different color. So this force, so we're just going to call this our pivots. Now we need to consider how far away are we. So if we look at this direction, this force is going to be at x away, and then this force is this distance right here over 2 is where our ladder is. So here, if the ladder is length L, this side would be at L over 2 this way. All right, so let's write out our equations of motion. So first one, let's look at all our x components. So this one's the simplest one. So we have our friction forces to the right minus the force of the wall, and then that's equal to 0. So the next one is our y components. So here we're going to have mg, the normal force between the ladder and the ground, and then minus mg, so the ladder is a little m, and then the person is going to be a big M. So we can go ahead and put these in. And then this all is equal to 0. So we can go ahead and realize that this is equal to 2m, and so then we can go ng is going to be equal to, here's 1 plus 2, that's 3mg. So the normal force applied by the ground is equal to the force of the ladder pushing down and the force of the person pushing down. That's not that remarkable. Okay, so the next part is going to be the torques. So we're going to pick this part to be our axis of rotation. So now we need to think about how far away each of these forces are, and then also make sure that we're getting the right x component, basically. So let's do the person first. So the person is x distance away, so that's x, and then the person is 2m g. So this is the force, this is the distance. Now we need to make them perpendicular. All right, and if we wanted to find how far up the ladder they're going, we're going to say that this distance is x. So they're going x up the ladder, so that's going to be x times, basically we want this component. We want to make these two perpendicular, so we're going to have a sine theta. And then now we do the ladder, so that's L over 2, and then times mg, and then now a sine theta again. And then now we have the wall. So that's plus, sorry, this guy's a minus 2. So here I'm saying that this way is plus tau. So only this guy is trying to rotate the ladder this way. Both these forces are trying to rotate the ladder clockwise. So now we're going to have L times the force of the wall, and then sine of, this one is actually going to be 60. So these are both 30, and then equal to 0. So be careful to check the angle between both of each of these forces and the moment arm. So here's the moment arm, here's R, and then now what we want is we want this component of it. So if this angle is 60, then this angle is 30. And then what we have to do is look at what is this angle right here. And if you work it out, you'll get that's equal to 30 also. Or so cosine 30 is the same as sine 60. All right, so let's try to solve these guys. So we have quite a few unknowns. We don't know what FW is. We don't know what this is. Let's change color again. All right, we don't know what this is. We don't know what X is. Now that we know the normal force between the ground, that's good, but we also don't know what this is. So let's try to plug in a few things. So looking at number 1 again, we have the friction force is equal to F wall. So another thing that we know about the friction force is it's equal to mu times Ng, this normal force right here. And we know that Ng is equal to this. So we're going to type in mu 3mg is equal to F wall. So that's good. So we got rid of one of these guys. So this is equal to Fw. So we can use this to be able to plug into basically number 3 again. So we've used both 1 and 2, so now it's our turn to use 3. So now we're going to plug in, we got minus x 2mg sine 30 minus L over 2 mg sine 30 plus L, and now I'm going to stick in this mu 3 mg sine 60 equals 0. So I'm going to plug in just what this sine 30 is. So this right here is equal to 1/2. So that makes that pretty simple. Sine 30 is also 1/2. And then this is equal to square root of 3 over 2. So I'm just going to plug these guys in and see what I get. And then I'm also going to bring these two negative terms over to the other side. So now I'm going to get x mg plus mg over 4 is equal to mu square root of 3 over 2 g, I guess. And then also times, also times 3. And then m, don't forget that. So each of these terms also has an L. I can get rid of that. I can also, so this was XL, well, X over L. And then I can also get rid of each of these M's. So I'm just going to get rid of the M, and the G's, and then see where that takes me. So now I'd like to get X, basically X over L is going to give me the fraction of the way up. And I'm just going to solve for that. So I need to bring this guy back over. So what I'm going to get is this 3 square root of 3, then times my mu, which is 0.45, and then now divided by 2, and then minus 1/4. So this gives me 0.92. This is how far up I was able to go up this ladder. So basically I can go all the way up to stand at 92% of the length of this ladder. And then if I go any farther than that, it's not going to have enough friction to keep me from slipping, and so then I'm going to fall. So, but I will be safe as long as I stay on this side of this 0.92.